Да, здесь странно, что я должен там себя видеть больше, когда стоит.
Она выглядит вот ровно. Вроде какие-то виды надо отключить, что вот эту доску отключить, это отключить, камеру включить.
Нет, надо включить две доски и надо включить отдельный телевизор. И вот отдельного телевизора здесь есть виды. Ну, вроде как стандартно всегда работает вид номер 2. Я сейчас как-то пользуюсь, но пока никак не реагирую. Сейчас, может быть, еще камеру надо включить и выключить. Может, вот это сюда. О, вот это похоже на то, что должно быть. По крайней мере, меня видно. Надеюсь, это Okay, so we continue with the following situation. I have a category, so S. This is curly S. This is compactly generated regulated category. And I have notation for the set of generators. So S, which is just the standard S, is inside the category. So I'm trying to kind of write it differently. S for the generators and S for the categories. This is the set of compact generators. Set of compact generators. And we study the following situation, which is sometimes in the literature called the Thomason localization, meaning that I take some set R of compact objects, so not just the subset inside the compact objects of the category S, form a category R, which is the localized enclosure of the set R. That's a subcategory inside S, and then I consider the quotient. So here I have factor from the category S to the category T, which is by definition the quotient of the S by R. And I also want to give a name to this one. I want to call this J with the alpha star. So the last lemma that we looked at the end of the previous lecture actually can be reinterpreted again if we use this statement with the 6 equivalent points. We can say that factor J upper star admits a right adjoint. Right? This followed by the previous lemma, because in the previous lemma we proved that there is a triangle of a special kind, and that was condition 6, and that in that statement with 6 equivalent points, and another condition that this functor admits a right adjoint. So there is a right adjoint, and if you analyze it a little bit more closely, well, the object that we constructed in the proof, the homotopy colimit, right? So I think I called it Y. So that was one of the objects in the distinguished triangle. But you also know that that distinguished triangle is functorial, and the object Y is actually just the J upper star and J lower star. So we can notice that from the proof of the previous lemma, we have this conclusion. So this Thomason localization, this situation of this, is actually a Bostock localization, right? So Bostock localization means that the quotient functor, J upper star in this case, needs a right adjoint. So we continue to study these properties of Thomason localization. So first,
how we get that it has a right adjoint?
well, because the lemma construct this triangle of special kind, right? We have this distinguished triangle, and that's the triangle that we have in condition 6 of that. six equivalent conditions.
Yes.
And from that I can conclude that there is a right adjoint, and even more that there is such formula for the composition.
And we have constructed a special triangle
Yeah.
in the previous lemma.
Yes, exactly. The previous lemma there was a claim that if you start with any object in the S, right, then you can map it to an object Y, which is in the right orthogonal, and also the tone is from R. Okay, so the next statement is quite easy, but it still kind of indicates several more properties, so I want to call this theorem. So the first part of the theorem is that the right orthogonal, right? We can think about this the right orthogonal, or since we know that we have the situation of the Boswell localization, we know that the right orthogonal is also the same as the category T. So this thing is compactly generated. I'm going to write CG for shortness. And the set of compact generators is just the J upper star applied to the set S. Notice again the different fonts. This is just this set of compact generators, this is not the category. So R2 of the theorem, subcategory R is compactly generated. And the set of compact generators is just the same set R that we used to divide this subcategory. Great. In a special case of 2, if R is just S, this is classes, also actually sets of objects. So then R is equal to the S. Right. Notice that even 3, this is not a completely trivial statement, it requires some short proof. Okay, so let's prove this. So 1. So I want to show that this is compactly generated, right? So I just look at the home in the category T from the J upper star S applied to some object, say X. Right, so then condition so that this is equal to 0, right? This of course just means that I take any object in the set S, apply J upper star and plug in it as the first argument. So this condition that this is equal to 0, I want to show that this is equivalent to the condition that X is isomorphic to 0. Well, there's a sequence of equivalences. This is equivalent just by adjunction that the home over category S from the any element in the set S to the G lower star of X is equal to 0. And now this is set of compact generators, so this is equivalent to the J lower star of X being isomorphic to 0. And finally, I want to say that this last condition is equivalent to the X isomorphic to 0. So the question is, so I think the first two equivalences are completely trivial. This one isn't less trivial. So why you have J lower star is equal of X is isomorphic to 0 if only if X is isomorphic to 0. Well, because the J lower star provide you an equivalence with the J lower star. This is a functor from T, but this is functor from the R right orthogonal, and that's an equivalence of categories. Again, by that lemma with 6 points. Hence, if you apply this functor to something, then you get 0, and the object is 0. Okay, for 2, let me take an object little r in the category R. Such that home from the set R to the little r is equal to 0. So I want to conclude that this little r is actually 0.
Why do you know that G star S is a compact object?
Hmm?
When we speak about compact generators, we need the objects.
That's true. That's true. We don't know yet that these are compact objects. We will prove this a little bit later. So maybe let me put this in parentheses. So later it will be compact, but at the moment we put that it's generators. Okay, for 2 I want to consider a situation where such form is equal to 0. Now I can notice that since I have this form, so I can say that the set R is contained in the left orthogonal to the object beta R. Right? But left orthogonal of any class is a localizing subcategory. So hence, subcategory curly R is also contained in the left orthogonal to the R. And finally, since R is in this, you choose this in this subcategory R, we have that R is contained in the left orthogonal to the R. In other words, home from R to the R is 0, so R is 0. So that's the proof of the second point. And finally, the last one. So we have, since we have this inclusion of the set S into the set category curly R, curly R, then we can take the right orthogonals, and for the right orthogonals there will be inclusion in the other direction. So the right orthogonal to the R is contained in the right orthogonal to the class S, right? But the right orthogonal of the class S is actually 0, right, by the assumption that S compactly generate. Sorry, when I was making the amendment, this is of course correct. So to assume what I need to change is the statement 1. So this thing is generated by this. Yeah, so we see that the right orthogonal of the category R is 0. But now we have a situation of the Bostrom localization, right? We know that the quotient category, so S modulo R, is actually equivalent to the right orthogonal, which is 0. Hence, this category R coincide with the category S. Okay, that's the proof of this small theorem. Now for the next several proofs, I need one technical definition. So it's not very interesting in general, but it is useful for the technical purposes. This is a notion of length. So say if object E is a direct sum of objects of R, we say that by definition the length of such E is just equal to 1. And if you have a distinguished triangle with the E prime, E in the middle, and E double prime, so that's a distinguished triangle, then we by definition say that the length of the E is equal to the length of the E prime plus the length of the E double prime. So the length is additive using distinguished triangles. So then, a lemma.
Okay, can you explain the last step in support after we get that S orthogonal is 0?
That orthogonal 0 is just more or less given to
Yes,
us.
and the next step.
So the conclusion is that the right orthogonal is 0, hence this quotient is 0. Right?
And why we know that this quotient is are orthogonal?
Again, by that lemma with 6 points. One of the equivalent conditions, since you have this Boswell localization, you have right adjoint, this is equivalent to saying that the quotient or quotient category is equivalent to the right orthogonal.
Is length 0 equal to 0?
Well, length 0, we can say this is just a 0 object. But I don't really care about the length 0, so for me the length will be 1, 2, and any natural number. Okay, so in the next lemma, which is kind of technical lemma that we're going to use in the other proofs, so we assume that we have a diagram. It would be nice to write this with different colors, but I'm not sure how I can do this. Maybe I just waste my time trying to do this with different colors. So let in the diagram, so the diagram is given. I have a distinguished triangle with y prime, y, and some e. So that's a distinguished triangle, and I have also object x. So let in the diagram the kind of lower part be distinguished triangle, and the object x that we have in the diagram is the compact object in the category R. And the length of the object E on the diagram is finite. So then we kind of can extend this diagram and construct the following. We have x prime mapped to the x, then there is f, that's a distinguished triangle, and there is a map of distinguished triangles. X prime is mapped to the y prime, x is mapped to the y, and f is mapped to the e. So then the upper part of the diagram is the new distinguished triangle. The object x prime is again a compact object in the category R, and also f is in the thick closure of the set R. Okay, so starting with this data, we can extend this to this data with these additional properties, assuming that we have this and this. Okay, proof. The proof will be by induction on the length of E. By induction on the length of the object E. So first, we consider the case when if length of the E is equal to 1. So then, in this case, we have a map, right? So we have a map from the x to the E, and we assume that x is compact. So map x to the E, and in this case, since the length is equal to 1, E is just a direct sum of objects. So this map factors through finite sum of objects of R, right? Since X is compact and E is just some direct sum of objects, we're using that kind of home to the infinite direct sum can use with the direct sums. we can conclude that there is only finitely many objects.
Excuse me. It's clear that length is well defined, and moreover, I think we should allow it to be negative. Because we can shift this triangle, and then we will have different triangle and different equality length for shifted.
And what happens for the shifted?
So here, length of E is, for example, larger than L of E double prime. But we can shift this triangle.
Yeah, so let's do this. We have E, right? Then E double prime, right? So then there will be E prime
Shifted by one.
shifted by 1. And, well, then we have this.
And in this case, L of E double prime
Yeah. We still want this equality, right?
Yes.
Since I assume this point distinguished triangle, but what it tell us? Well, I think it just tells us that the length of the shift of this thing is just the minus of the length.
Yeah, so it's negative. So we need to somehow. So we cannot just simply do induction. We need to do it in both sides or something like this.
I don't understand. If we have an object of R, then its length is 1 always, right?
Yeah. So not just object of R, just any direct sum of objects of R.
Can't it happen that E prime, E double prime, and E are objects of R?
So you mean in the situation where we have something like the split triangle?
So we have 1 is equal 1 plus 1 in this case, but it seems to be possible.
Oh yeah, of course this is possible. For example, we can take something like object in the R, direct sum another object in the R, and the quotient is another object in the R. But that's a trivial triangle, and in this definition I only want the non-trivial triangles. Is it possible to non-trivial triangles?
На утверждение же нужна не длина, а то, что длина не больше какого-то числа, по сути. То есть то, что можно построить цепочку из не более чем, условно, L от E штук, а не то, что она именно L от E. Может, разных там.
Yeah, so that essentially what I'm trying to do is that I need this statement, right? And I need the statement for any E of the finite length, which means that I can, the E that I can consider is the direct sum of objects in the R, something that can happen by an extension, 1 extension, 2 extensions, and 3 extensions, etc. For any finite number of extensions. So essentially the length is showing how many non-trivial extensions I'm taking to get an object E. Do you agree with it?
No, because I have objects with negative length, right? In this case, I can add object of length 100 and object with length minus 100, like E plus E shifted by 1. And I will get an object of length 0, which is, or even of length 1, which doesn't lie in R.
We can change the definition, like L is infimum of sums of L E prime plus L E double prime for all distinguished triangles. Then it seems that we don't have negative lengths.
Okay, yeah, this one is. So,
Maybe yes.
let's take that this is infimum of the sums of the E prime plus length of the E double prime such that we have a distinguished triangle. we still need to do the induction. So the first base of the induction, so I assume that I have object E, which is just the direct sum of objects in the objects in this set R. So then I already constructed this finite sum of objects of R. So I have factorization. So I have X factors through F, and hence in the diagram with the Y prime, Y and E, there is X mapped here, so there is also F. So I have a map from the X to the F, and I can extend this to a distinguished triangle. So let's extend this to the left, and so there is an object X prime. Right. And by one of the axioms of complete category, we have two maps like this. I have the map from the X prime to the Y prime. So the question is, since we want in this map of triangles have these two properties, so F is more or less by definition in the thick of R, we need to understand why X prime is the compact object in the RC. But that's easy, right? Because thick of R is contained in the RC. Right? So X is given to us that this is in the RC. Hence, if the two objects in the triangle in the subcategory, since this is a triangulated subcategory, the X prime is in the RC. Okay, so this is the base of the induction. Now, let's do the step of the induction. So, I assume that the length of E is some finite number n. And I assume that
why X prime in RC?
by the assumption, so let in the diagram X be in the RC.
No, X prime.
Well, because we have this distinguished triangle.
Yes.
Yes, so this is in the RC, this is in the RC.
How we defined F?
F we defined here. Right, we use that X is compact, right? So there is a map to this infinite direct sum, hence this factors with finite direct sum, and this finite direct sum is F. Okay, so I want to do the induction. So since the length of the E is not 1, so there is a distinguished triangle, E prime, E, and E double prime. So I want to call the map from E to the E double prime beta. And I have the distinguished triangle that is given in the condition with Y prime, Y, and E. Right, now I want to call map from the Y to the E alpha. So then for these two maps, alpha and beta, I want to apply the octahedral axiom. This is what I get. That's a distinguished triangle that starts with Y with the map alpha to the E. So then the next term is Y prime shifted by 1. And the next term is Y shifted by 1. Now there's a map beta to the E double prime. Now for this beta, the column is E prime with a shift. Right, so then we can claim that there is a distinguished triangle. So the Y prime shifted by 1, then the next object I'm going to call Y double prime shifted by 1. So then this is mapped to the E prime shifted by 1 and Y prime shifted by 2. So this is the octahedral axiom that I apply for the maps alpha and beta. So of course this map is just the composition of the beta in alpha. So from this octahedroaxiom, we have a conclusion that the map y prime to the y has factorization y prime is mapped to the y double prime, and then y double prime is mapped to the y. Yeah, well, we can, for example, see it here with the shifts, so we can unshift everything. Yeah, and these maps, so let's maybe give them names. So this is U and V. This is the maps in this diagram. So the maps U and V are in the Moore R, which you can again see from this diagram for the octahedroaxiom. Right, for example, where is U? Well, U shift of U is here, right? But the cone of this map is the E prime, and the E prime is in the R. Yeah, the same for the second map. Okay. Okay, I need to erase the statement. So then I can take a diagram with the y double prime, which is mapped to the y, right? So the map that we just constructed. So the cone of this map is the E prime of the small lens. Now I have a map the same as before from x to the y, and by the induction hypothesis I can extend this to the map of distinguished triangles. So let's call this f double prime and x double prime. So that's what we have by induction. So then I look at the triangle where I have y prime, which is mapped to the y double prime. So the cone is E prime from that distinguished triangle. Now I take a map, and since I know that when I do this construction, x double prime is in the RC and f double prime is in the thick R. So now I can use this x double prime for the next step. I take a map from the x double prime to the y double prime and complete this diagram to a new diagram. So I'll get x prime and I'll get f prime. Again, x prime is in the RC and the f prime that we have in this diagram is in the thick R. Okay. So together, if you kind of just take two squares and combine them together, you'll get the following. X prime is mapped to the x double prime, and this is mapped to the x, and x prime is mapped to the y prime, this is mapped to the y and x double, to the y double prime and x double prime. So I'm just taking the square from the second diagram and combining this with the first square from the first diagram. So we have x. So the thing that we want to construct is this one, right? So we already have this part of the diagram. I have a map from the y prime to the y and x prime to the x, right? So to conclude the proof, I need to show that the cone of this map, which is f, has the right property, which is just f is in the thick of the set R. And this is done again by the octahedroaxiom. So let me look at the octahedroaxiom for the following map. So let's call this map T from the x prime to the x double prime, from the x prime to the x, I'm going to call this map S. So then this is the composition, right? And the composition, right? So we exactly want to understand the cone of this composition S and T. So the cone of the map T is F prime. Now the cone of the map S is F double prime. So then we have by the hydroaxiom another triangle with new vertex F. Right. So this F is the cone of the map ST that we want, but also middle term kind of this distinguished triangle, and we can say that the F is then the thick of R, since the thick of R is triangulate category, and F prime and F double prime are already there. So that's the end of the proof of this lemma. Okay, before I erase the proof, questions maybe? Comments? Okay. So theorem. The compact objects in the category R is precisely the thick closure of the set R. Okay. Then let's take object X, which is compact in the category R. Well, we can kind of do the same thing as the lemma on the previous lecture. I can define x0 to be x, and then I define xn by induction. So let I be the set of all maps of the I from the yi to be xn, so this yi are in the set R. So then we have the following kind of tautological triangle. So I have tautological map from the direct sum of all yi's to the xn. I take the cone on this map, I'll get xn plus 1. Okay. Some shortage. So this is the definition of the object xn plus 1, and we can see that by the construction, this is an object in the R. So direct sum is in the R, xn is in the R by the induction hypothesis. So then if we take y to be the homotopic limit of the xn's, so I want to show that this y is a zero object. So first of all, you notice that this is in the subcategory R, right? Since every term in the homotopic limit is in the R. So then, as before, the home, well, I can identify, say, the limit, direct limit of the home, homes from the C to the xn.
What is the xn? And so you defined it using this little triangle.
Yeah, so xn is defined by induction by this triangle. x0 is by definition x, then you use this definition to define x1, x2, etc. So there's the direct limit of the homes from the C to the xn is the same as the home from the C to the y. And that is for any object C, sorry, not in the set R. Right, since such element C is a compact object. But then I just use the same logic as before, right? If I look at this distinguished triangle, I look at the corresponding homes from C to the direct sum of the yi. This is mapped to the home from C to the xn. This is mapped to the home from C to the xn plus 1. So the map here is 0.
Why we have this isomorphism between the...
Because C is compact.
But we know that the home commutes only with direct sums.
And there was a lemma that I left as an exercise. Probably should add this in the next problem. Actually, it was in the previous problem sheet, I think. That for the compact object we have at least, if you have a co-limit here, you can pull it out as a co-limit here. So this is what I'm using.
Yes.
Right, so then by the construction of this distinguished triangle, as this map on the homes here is 0, right? Hence the limit on the left hand side is 0. So, so we'll get that the home from C to the y, which is isomorphic to the direct limit home C xn, this is equal to 0. So we obtained the result that this home from any compact object in the set R to the y is 0, and we know, so then we can combine this with the previous observation and say that y is then the R right orthogonal, and hence y is in the intersection of the R and the right orthogonal to the R, which is of course 0. So object y is 0.
Why is the map 0 between home from C to xn to home from C to xn plus 1?
Well, by the definition, so all the homes that we potentially, all the, right, so all the maps that we, so you here you have all the maps from all the compact objects, right?
Yes.
To the extent they are already in this home, right? Now, if you take this composition, right, well, if you have any composition of this form, so this you take some form C from the R, if you consider what I'm doing.
So any home from C to xn comes from home to.
So you can notice that, for example, that this is an epimorphism, right? Whenever you have a map from the C to the xn, this is actually already in this home from the sum, right? Because here you have all the possible maps from the object C to the xn.
Yes.
Yeah, okay, so y is 0. And of course, you can also kind of, because you see this is the repetition of the lemma that we proved last time. So if you want, you can kind of skip this, right? And you can use argument with the functors, right? So you can write that this j low star j upper star is a homotopical limit. Use that j low star give you the equivalence of the r of the t and the right orthogonal to the r, and notice that this kind of, you can avoid this argument and use just the argument with the functors. But I'm not sure what's more convincing, so I decided to repeat the argument. Okay, so anyway, we have the result that y is 0. And then if we look at the 0, which is the home, say, from the x 0 to the y, so this is obviously 0, and also this is the direct limit of the x 0 to the y by the same argument as before. So then, from this I can conclude that there is a number n positive such that x0 to the xn is 0. Right? Because if this is not the case, then this limit can be equal to 0. Okay, so then I need to use another octahedral axiom for kind of one simple observation. I have a jn minus 1 mapped, we say with the map jn to the xn. So then there is a map to the xn plus 1 with the jn plus 1. And here I take the composition. So this is jn plus 1 jn. So the cone of the jn is some rn. So let's call the cone of this composition R. So then the cone of the jn plus 1 I'm going to call Rn plus 1. And then we have a distinguished triangle, the vertical distinguished triangle. Right, and in this vertical distinguished triangle, we can notice so from this we can notice that the map from the x0 to the xm is a finite extension of objects of, well, I need to say that of direct sums of objects of R. Direct sums of objects of R. Right? Because by definition, when we consider a cone like this, well, this is defined by that triangle, and hence this Rn plus 1, or any Rn, is actually a direct sum of objects in the R. Right? So then for the composition of two maps, I'll get that the cone of this map is this vertex in the triangle, but that's a kind of, for composition of two maps, that's an extension of the something of the direct sum of R and direct sum of R. And then the map from the x0 to the xn, or for any two indices I and j, right? This will be just a finite composition of such things. So this result by induction and this octahedral axiom. Okay. So maybe I can squeeze in just another argument here. So we have this map that we constructed from x0 to the xn, which is a zero map. And the cone of this map is E, and the length of E is finite. Since this is a zero map, this is a split distinguished triangle, so object E is isomorphic to the sum of the xn plus x0 with a shift by 1. Okay. So then I look at the following diagram. I have a distinguished triangle where I have E shifted by 1, E actually by minus 1, I think, yeah, E shifted by minus 1, 0. Right, so this is just the trivial triangle for the identity map. And then I have a map x0 to the E shifted by minus 1. Well, this is, if I shift this by minus 1, so x0 will be just a direct summand. So this map is just an inclusion of a direct summand. And this I can extend to a distinguished triangle and a map of distinguished triangles. So this is x prime with a shift. Well, I claim that when I do this, I necessarily get this map from the x prime to x0 to be a zero map, right? Because this composition is of course a zero map, since I can compute it like this, and this map is just inclusion of a direct summand. So the only possibility that this composition with inclusion of a direct summand is zero is that this map is zero. So this map is zero, and hence this is again a splitting triangle. So we can say that F, which is by the previous lemma, is an object in the thick R, and also by the splitting distinguished triangle, X is isomorphic to the X0 plus X prime shifted by 1. Right. But yeah, I'm using X0, but of course, remember that X0 is the same as X. So this is a thick closure, right? So F is in the, so this is the, so this is a thick closure, so this is closed under direct summands. So F is here, hence the direct summand, which is in this case is X, is also in the thick of R. So we get an inclusion in one direction, and this kind of was a hard work, but I think the inclusion in the other direction is trivial. So this gives us the inclusion that the compact objects in the R are contained in the thick of the set R. But in the other direction, well, since you have R clearly contained in the RC, right? Any object in the R is compact in the category S. In particular, this will be compact in the subcategory R, so there are less conditions to check. And this is by the one of the exercises that I gave you last time is the thick triangulated subcategory, right? Since this is thick, we can conclude that the thick closure of R is contained in the RC, right? So for this application, I'm using that RC is this thick subcategory. Okay. That's the end of this proof. So this, I think that's a very interesting statement, right? You take any compactly generated subcategory, choose just several generators, and of course you might be interested what are compact objects in this subcategory. So the answer is quite explicit and simple. This is just a quick closure of the generating set. Okay, so then for the next theorem, I need a simple lemma. So simple lemma. I think that was what was missing in the first theorem today, that if you consider functor J upper star, right, that was a functor from the S to the T, and I'm just write this in terms of formulas. You take the compact object in the S, then this will be a compact object in the T. So in words, that means that J upper star maps compact objects to the compact objects. Right, so if we prove this lemma, also the result that I stated at the beginning of the lecture, the first theorem also will be correct. Okay, so the proof is just a kind of straightforward computation by the adjunction. So I take X, which is a compact object in the category S. I look at the home in the category T from the J upper star of the X to some direct sum. Right, I want to show that this commutes to this direct sum. Well, by the adjunction, I just rewrite this as the home in the category S from the object X to the J lower star applied to the direct sum. And now, the key step is that I actually can commute this J lower star to the direct sum. So this is the home in the S between X direct sum J lower star of the Y bar. can compute this functor J over star with direct sums.
Because it is like values of
Exactly, yes. Because by the same argument, J over star is an equivalence from the category T to the R right orthogonal, so hence it preserves the coproducts. And then the rest of the computation is again kind of tautological. So you can, since X is compact in the S, you can pull out the direct sum. You'll get on in the S X J lower star of the yi, right? And then just use the adjunction one more time. I'm sorry. Use the adjunction. So that's the lemma. And next theorem. So the induced functor from the quotient of the S, so compact objects in the S by the compact objects in the R. So we know that this will be a functor to the compact objects in the category T. So this induced functor is fully faithful. So we're going to prove a little bit even stronger statement. So what we will show is the following. So we show stronger statement, namely the following. If I take any X which is compact in the category S and any Y which is just any object in the category S, so then the map from the home S module RC X Y, so there is a canonical map induced by the functor J upper star to the home in the category T. I'm going to use the same notation for the objects. So this map alpha is an isomorphism. So let me write here. Map alpha is isomorphism. Yeah. For the proof, I also will need the following tautological observation. Of course, if I just write this less naively, I can write this as a home in the category T, J upper star applied to the X, and J upper star applied to the Y, right? And then use the adjunction to write home in the category S from the X to the J lower star to J upper star of the Y. And I know that the J lower star, J upper star applied to the Y can be computed as the homotopical limit of the objects Y. So the same procedure that I used in the end of the previous lecture, and also in some sense in one of the proofs today. So this kind of rewriting this map alpha will be helpful in the proof. Okay. So first of all, when we construct this homotopical limits of the Yns, well, you'll get, say, Yn mapped with the map Jn to the, maybe Jn plus 1 to the Yn plus 1. So cone of this map Jn plus 1 is indirect sum of objects of R. And now I take a compact object X, right? So take a map from the X to the Y. So X is compact. So this map this map from the compact objects to the homotopic limit factors through Yn for some n. So now I want to look at the diagram where I have y0 mapped to the yn. So then there is a cone, and then I use the argument as before. So since I know that the cones of all such maps are direct sums of the objects of R, I use that hydro axiom as before and get the conclusion that the length of the object E that I have here is finite. So then there is a map X, map from the X to the Yn, and I can extend this to a map of distinguished triangles. So there is some x prime which is mapped to the y0, there is some f which is mapped to the e, and we will know that in this diagram f is in the thick closure of the R. Yeah, so this is in the closure of the R, and we know that this is the same thing as the RC, so compact objects inside the subcategory R. So then in this diagram, we can notice that the map from the x prime to the x is isomorphism. So is an isomorphism in the quotient category, so in the S modulo RC, right? Since the cone, this F is in the RC. So in the quotient category, this is an isomorphism, right? And then, so then the conclusion is well, the conclusion is that alpha that we constructed before, right? So that was a map from the X to the. Okay, let me say that alpha is an epimorphism, and then I'll try to explain this, right? So what we have, we start with the map from the X to the Y, right? This automatically produced to us a map from the X to the homotopy colimit to the Yn, which give us a map from the X to the Yn. And since kind of in the quotient category we can identify these two objects, well, there is a map from the X prime, which is the same as an X in the quotient category, right? So to the Y0, which is again Y. So this is how we can lift the map from this home or this home to this home. So this proves that alpha is an epimorphism. Okay, now I need to go in the other direction and show that this is a monomorphism. Okay, so let's take a map X to the Y. So be a map such that is 0 in the category T. So then the map from the X to the homotopy colimit of the YNs is 0. And again, I'm using that X is compact, so I can factor this as a map from the X to the Y0 to the Yn. So this is 0 for some n. Just think about this as a simple exercise about the colimits. So then I look at the diagram. I have map Y0, this is mapped to the Yn. So then I want to complete this to the distinguished triangle, but now I want to write E on the other side, so let E be on the left side. So that's a distinguished triangle, and in this distinguished triangle, by the same argument that we used several times already, the length of E is finite. So the length of E is finite, and there is a map X to the Y0, and the composition to the Yn is 0. So hence, I can take this distinguished triangle, apply a functor home from the X to something, I'll get a long exact sequence, and from this long exact sequence, I can see that there is kind of lifting of this map X to the Y0 to the map X to the E. So this can be lifted. Okay. So now I look at the diagram where I have 0, E, the same E as before, just the identity map and this trivial distinguished triangle, and I take a map from the X to the E. So I can use the lemma that I took, so everything is fine, X is compact and E has a finite length. And then I can extend this to a diagram. So there is X prime here, the map, there is some F map, and the sheet. Okay, so in this diagram, as usual, F is the closure of the R, which is the same thing as the compact objects in the R. So, using more or less the same logic as before, X prime is isomorphic to the X in the quotient category, so in the S modular RC. Right, so then since the map from the X prime to the E is 0, we can conclude that the map from the X to the E is 0 in the S modulo RC. Right? So then in this, so this map from the X to the E is 0, and also this composition is 0. So by looking at this diagram, we can say that the map that we started with, the map from the X to the Y0, is 0 in S modulo RC. Okay. So that's the end of the proof. So we proved that this is monomorphism, and we know that it's epimorphism by something that we proved before. So that's a fully faithful functor. Okay. So the last theorem in this sequence of theorems tells us that the compact objects in the quotient category, so TC, this is the closure of the J upper star applied to the subcategory of the quotient objects, so to the compact objects in the category S. So in other words, what this means is that if you have a compact object in the quotient category, you can find for this object another complementary compact object such that the direct sum will be compact objects in the category S. Okay, so let's prove this. The proof is much more elementary than the previous one. Okay. So combining what we have proved already, I can say the following, that the category T, which is the same thing as the right orthogonal to the category R, is now compactly generated by the set T, which is the J upper star applied to the set S. Right? So we know that this set generates, this is what we proved in the very beginning, and we also proved that if I take a compact object, apply J upper star, I get a compact object. Okay, so then I can also notice that there is a clear inclusion. So this T is contained in the J upper star of the compact objects of the category S. So notice that this is the set and this is the category. Okay, so the compact objects in the category T, I can write this, since this is compactly generated, and we prove that for any such category, I can write this as the thick of the generating set. So in this case, this is T. Right? Clearly, this, since T is a subclass, or subset in this case actually, in this image, so then this is contained in the thick of the J upper star applied to compact objects of the category S. And this gives us inclusion in one direction. And the inclusion in the other direction is even easier, right? Because the J upper star of the SC, we already know that this is contained in the TC, right? And TC is the fixed subcategory, right? Hence, if I take thick closure of the J upper star of the SC, then this is contained in the TC. So that's the inclusion in the other direction. So essentially this finishes this discussion about the Thomason localizations. So we proved that the Thomason localizations have several nice properties about the compact objects in the set category, compact objects in the quotient category. But this last result, later when we know algebraic geometry, we will need a little bit more specific version of this. So this tells us that you take a compact object in the quotient, there's a complementary object, essentially the sum is compact. I want to show that actually for a compact object X, you can add X shifted by 1, and this sum is already compact in this. And to do this, I just need a little bit of K-theory. So just K0 of triangulate category, and maybe I leave something as the exercise. So just a brief reminder how the K-theory works. You can take any abelian monoid, so M, this is abelian monoid. So then you can construct f of M, so this is the free abelian group on this monoid, and so generated by the abelian monoid M. Then there is a kind of the subgroup E of M. So that's a subgroup generated by all the elements of the form class of X plus Y minus class of X minus the class of Y. So, and then finally, the G of M is defined as the quotient of the free abelian group by the E of M. So this definition makes sense for any abelian monoid, but we're going to use the following situation. So we take A to be any additive category. And for this additive category, I'll introduce monoid, let's call this G plus of A. So this is abelian monoid with elements isomorphism classes of objects in A, and operation is just a direct sum. By the way, notice that since I anticipate application to this the category theory, I also wrote this plus as an operation in the monoid M, right? So this is just abelian monoid with the operation, so maybe I can squeeze it here. So the name for the operation is just the plus direct sum. Okay, so then in this situation we just for shortness write f of the additive category to be f of the G plus of the A. E of the additive category is just the E of the G plus of A. And finally the group G of the A is just the G of the G plus of A. Okay. So then there is a kind of standard lemma. I think I'm not going to prove this. So if you have, just in general, or maybe just for additive categories, but I think this also works in general for any monoid. So for x and y objects in the A, the class of the x is equal to the class of the y in the quotient G of A, if and only if there is an object Z in the A such that x plus z is isomorphic to the x plus y.
Y plus C, right? Y plus C, right?
Yes. Okay, so I'm not going to prove this since it's really just a statement about monoids. But if you haven't done this before, I recommend you to do this as an exercise. Since it's not part of this course, I assume that you know something like this. I won't give this in the assignment, but I think if you haven't seen this before, it's an interesting exercise. I think there is a kind of room for surprise when you solve this exercise. So it's not a tautological statement. The proof is simple and just requires the knowledge of monoids and abelian groups, but it's not a complete reality. Okay, so let's take a 10 minutes break.
А классы изоморфизма не всегда же множество образуют?
Ну, вообще говоря, не всегда, да. Но в разумных ситуациях все-таки образуют. Ну, это то, что называется существенно малой категорией. Когда классы изоморфизма образуют множество. Насколько я знаю, более-менее ясно, в общем, что категории модульных кольцом такие, категории кружков над топологическим пространством тоже такие.
Почему тут Тау-Си это такие?
Вот здесь.
Да.
Я использую то утверждение, которое мы доказали там, для... У нас было такое утверждение для R. Да.
Для R, да.
Да. Я использую здесь такое же утверждение только для Тау. То есть вот утверждение для этого, более-менее говорит, что если вы берете и порождаете категорию как какого-нибудь популяризующего, да, то компактный объект, там это толстая оболочка генератора. Вот. Ну, в частности, это, например, там можно делать не для подкатегории, а это можно делать для всей категории. Если у вас есть там какая-то категория, у вас есть компактные генераторы, да, то тогда вы лучше, что вы берете множество компактных генераторов, получается как раз компактный объект в этой категории. Вот это оно. Это мы, короче, я это не смог записывать, но я это объяснил. Вот мы в прошлый раз доказали теорему, что у нас там есть любой объект из S управляется выкрик, такой, что там есть конус из R.
Ну, тобто специальный...
Да. Да. И ну, теперь, если вы посмотрите не формулировку утверждения определенного шестикомнатного доказательства, вы увидите, что как бы, в этом выдан другой объект, который соответствует Y, да? Да. Он как раз вот имеет всегда вот такую форму, что это функция и практика.
Можно так настроить. Тогда мы еще не знали про кокаин. Когда доказывали вот теорему в 6 пунктах.
Не знаю, конечно, это не утверждение, это правильное утверждение такое, что вот вы построили выгодный треугольник, где у вас там один из категорий, второй из правого ортогонального категории, да? То из лемма следует, что то, что находится там...
Из какой из лемма?
Из 6 пунктов, да.
Это вот из той теоремы,
Да, если вы посмотрите на доказательства, это на самом конце. Да, вот это теорема. Ну там, в общем, там смысл в том, что вот эти моменты, которые у вас есть в пункте 6, да, в пункте 6, это не указано, на самом деле, эти треугольники, они как бы имеют вид специальный. Что там, грубо говоря, вот эти одно проблемы, то есть это единственный да, что на самом деле треугольник, который у вас существует, не вот такой. Но также просто, как бы, смотрим на треугольник, который мы построили, там в этом треугольнике будет объект Y. Ну, где обозначается лемминг с помощью
если мы берем вот этот Y, строим вот этот объект, да. То есть в качестве или он выглядит.
Нет, ну, если взять эту лемму, которую мы доказывали на прошлом занятии, там было отображение из X в Y, да?
Да.
У вас будет отображение из икса в Y, да? Y находится в параметре диагонали, ну а конус этого морфизма находится R. Да? То есть это как раз правильный треугольник. То есть как бы такой треугольник, как бы в условиях есть. Дальше вы построили эту легкую, то есть доказательство, как мы его строим. Это соответственно, вот у вас есть выделенный с правильными скобками, у которого сомнительно должны стоять сейчас между сверху звездочкой. Там, соответственно, стоит математический попредел. Значит, математический попредел, это вот они есть теории, они реальные, естественно.
Да, он гомотопический, получается, не просто предел.
Я думаю, метафизический, что я могу.
Да. И из этого мы получаем, что они одинаковые. Изоморфны.
Да. Но потому что такие виды треугольники, они не с точностью зависимости от категории F.
Да. И вот еще вопрос про то, что мы использовали здесь вот, что функтор G со звездочкой снизу, он является эквивалентностью категории. А здесь между вот фактором и этим, это из какого этих пункта следует? То есть это ведь мы про третий пункт, но только он про Q. То есть про G вначале, потом Q, он получается.
Нет, но у вас есть как вот это Q, да? Это эквивалентность категорий, но это будет эквивалентность категорий в другую сторону. А обратно к нему это будет как раз стоять право сопряжения.
И здесь получается нужно сказать, что он попадет туда, куда нужно.
Ну, так или иначе, вот это линия, где-то есть.
Вот линия вот в этом стоит.
Да. Ну, уже по поводу утверждения, что у вас есть эквивалентность категорий между, грубо говоря, есть у вас правый канал K, фактор, и эта эквивалентность, с одной стороны, дается на позиции, с другой стороны, она дается как бы функтором, который правый сопряжение. Так или иначе, если это спрятано,
вложение вполне строгое, и функция сопряженная, вот этот G с нижней звездочкой, может быть, просто есть сопряженность, эквивалентность G с сопряженностью, она тоже сопряженная функция, тоже.
Ну да. Может, так или иначе, это очень обязательно.
То есть это вот это с третьего.
Да. So the last thing that I think when I discussed this Thomas localization was that so you can give you had this result that the TC is the closure of the J upper star of the SC. So for example, I will be interested in the situation where I have like at this level. So suppose I have A inside B. So these are just inclusion of additive subcategories. So strictly for additive subcategory, strictly for additive subcategory, such that I want to write this something like the fig of A is equal to B. But for additive categories, people don't use this notation, so just write this with words. So such that any object of B is a direct summand of A. So the assumption is more or less just to, but we will need potential application of the results that this lemma and the next couple of statements to this situation. So this is why I want to consider this situation. So then, with this assumption, I have a quality. I take E of the subcategory B. I intersect this with the F of A, and then I still get E of A. So that's the statement. That is just a technical statement that we're going to use later. Okay. So first of all, we can notice that any element of the G of A first of all can be written as the difference of the class of X minus the class of Y, whereas X and Y are two objects in the category A. Alright, this is just follows from the more or less the definition of the GA. So then any element of the F of A, right? So the G of A is the quotient of the F of A by the E of A, is of the form this difference plus some V, well, where this little v is just an element in the E of A. So I'm taking element in the F of A, and if additionally I assume that this thing, so the class of X minus the class of Y plus this little v is in the E of the category B. So then I can say that just the difference of the X, class of X and class of Y is in the category, is in the group E of T, right? So why this is the case? Well, so this is because I have this V, right, which is in the E of A, but the E of A is contained in the E of B, right? So if this sum is in the E of B, and this is just some abelian subgroup, right? So V is already in the E of B, then this difference has to be in the E of B. Okay. So if this difference is in the E of B, then it means that this in the G of B, these two classes are the same. Hence, I can say by the previous lemma that there is an object Z in the category B, such that X plus Z is isomorphic to the Y plus Z. And also, by the assumption, so I never used the assumption that any object of B is a direct summand of object of A. So by the assumption, I can also say, there is another object, Z prime, in the B, such that Z plus Z prime is in the subcategory A. So now here I'm using the assumption of the lemma. Hence, x plus z prime is isomorphic to the y plus z plus z prime. Right. So then, if we look at the difference again, so x minus y minus y, so this is in the E of A. Right, again, look at the classes, you move x minus 1 on one hand and you move all the z's on the other hand, but you move just basically this sum of two objects to the other hand, and this will be in the E of A. So this difference will be in the E of A. And this improves the inclusion in one direction, right? If I take something in the intersection, I can always write it as this difference. This will be an object in the E of A. And of course, the inclusion in the other direction is completely trivial, right? Because E of A is contained in the E of B and clearly contained in the F of A. So the other direction is trivial, and that's the proof of the lemma. Okay, now I want to define let me keep the notation and let's say that A is now.
Why is there Z prime? Why is there Z prime such as Z plus?
Because of the assumption. So I assume that this is kind of the closure of A is B, if I'm using this for triangulated categories. Okay, so now let me say that A is triangulated category. So then for triangulated category, I can define the K0. Maybe I need to write this as a definition. So definition, let A be a triangulated category. So then K0 of A, so the K0 of the triangulated category is defined as the quotient of the F of A modulo the relations, so where I take the class of Y minus the class of X minus the class of Z for any distinguished triangle. Is like this, and I need to write such relation for any x, y, and z being a distinguished triangle. So before we only use the additive structure and the fact that we have direct sum of two objects, and we define kind of the very elementary version of the K theory, which is just the G theory for the functor G. And this is now something that has information about all the distinguished triangles. So any distinguished triangle give you kind of a relation, and we need to take a quotient by this relation of the F of A and get K0 of A. Well, of course, it is clear that we have a canonical map from the G of A to the K0 of A, right? Because we just add more relations, and this is an epimorphism of abelian groups. And also there is some kernel. I'm going to denote this kernel I of A. So, by definition, I of A is just the kernel of this canonical map. So, proposition. So, let, as before, A inside B be a subcategory, but now I want to assume that this is triangulated subcategory. And the same condition as before, that the thick closure of A is equal to B. Right? Sometimes this situation is called that A is dense in B, if the thick closure is equal to the B. So then we have several observations about these groups. So first, G of A to the G of B is mono. So that's a monomorphism of Abelian groups. 2, if you look at the I of A, which is mapped to the I of B, this is an isomorphism. And finally, 3, K0 of A is mapped to the K0 of B. This is again monomorphism. So, the following 3 observations. Okay, so let's start with the first one. So suppose I have, first one. Yeah, the first one. So let's take X to be in the kernel of the map from the G of A to the G of B. Right? So, but this means that this X is an element in the U of B, right? Since this is supposed to be 0 in the GB, so this has to be in the E of B. And also, this is in the F of A, which we know to be the same as the E of A. Right? But if the X is in the E of A, we automatically get that the class of X is 0. So that's the proof of the first statement in the proposition. That's the monomorphism. Now, I automatically get that the map.
How we conclude that X lies in this intersection?
Well, because if X is in the kernel, first of all, this X has to be in the F of A, right? So because we consider some class of this element X in the G of A.
Yes.
So it can be represented by some object in the F of A. Now you kind of map this to the G of B and you get 0. But if this is 0 in the G of B, it means that though G of B is just a quotient of the F of B by the E of B, so it means that this is here.
Yes.
Hence this is in the intersection. Well, if you just, maybe I write the diagram for the snake lemma. So you have the 0, I of A, G of A, A0, A, and the same for the B. So then there are induced maps between these 3 groups. So what we know already that for the G, this is a monomorphism, right? But immediately the snake lemma gives you that the map on the ice is also a monomorphism, right? So by snake lemma, I of A, the I of B is monomorphism. So we need to show that actually this is an epimorphism also. Okay, so to show that this is an epimorphism, let's consider the distinguished triangle. So X, Y, and Z. So this will be a distinguished triangle in the category V. So it gives us kind of the element y, class of y minus the class of x minus the class of z. So this is in the I of b, and moreover this group I of b is generated by such classes, right? So to show that this map is an epimorphism, I need to kind of lift any generator from this group to an element here, right? Such I need to find an element such which is mapped to this generator. So any generator of the IOP is on this form, but some distinguished triangle in the category B. So we can take some x prime and some z prime in the category B, such that the sum of the x plus x prime is in the A, and the sum of the z plus z prime is in the A, right? So this we can do by our assumption that phi of A is equal to B. So we have these two objects. And then we add three distinguished triangles together. So let me write this maybe in words. So add distinguished triangle with the x prime identity map x prime and 0. So we have one tautological distinguished triangle. Then another tautological distinguished triangle with 0 z prime identity z prime 0, which is plus 1. Right, so this is another tautological. And the given distinguished triangle x, y, z. So we get, when we take the sum of three distinguished triangles, triangle x prime plus x mapped to the x prime plus y plus z prime, and this is mapped to the z plus z prime plus 1. Okay, so now in this distinguished triangle, I know that these two objects, x prime and x, z and z prime, these are from the A, right? And since I assume that A is a generated subcategory, I claim that this middle term is also in A. So this is in the A. But this means that if I look at the element kind of relation given by this distinguished triangle, which is just the x prime plus y plus z prime, so the class of this minus the class of the x prime plus x minus the class of the y prime, sorry, or z prime plus z, z prime plus z. So this thing is in the E of A. So, and its image in G in E of B, I of B is precisely the same relation that I have in the beginning, right? So this is let me call this star. So the star is this element in the I of B. So hence, we have the isomorphism. Okay. So generators in the IOP are of this form, these differences for distinguished triangle, and I just for any generator I found an element in this group such that this is mapped to this generator. So this is an epimorphism. So finally, part 3, I think that this is more or less clear, right? Since again, this is by the snake lemma, since we have isomorphism here, right? So imagine that we have kernel, 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 then this is mapped to the co-kernel, this co-kernel is 0, there is no kernel here, hence there is no kernel here. So by the snake lemma, again, by snake lemma, K0A is a monomorphism to the K0B. So we have another group. Okay, so finally, the interesting statement, not not a technical one, but really something that have applications. So let me assume that I have a situation as before. So theorem. Let A inside B be a triangulated subcategory such that the thick closure of A is equal to B. So dense subcategory in other terminology. So then object X in the B is in A if and only if the class of X in the K0 of B is in the image of K0 of A. Well, first of all, look at the statement and now it doesn't make sense what I'm trying to say. So in this situation, I have two triangulated subcategories and A is dense inside B. I can decide whether an object from B is actually an object from A just by looking at the K0 classes. So that's what it tells. Okay, so for the proof, I look more or less at the same diagram, right? Maybe I just rewrite this. So I have this diagram, and this is an isomorphism with I of B. Then by using the snake lemma, well, maybe I introduce some notation. So let me call I to be the functor from the A to the B. So then this will be the J of I, and this map will be K0 of I to the K0 of B. So, and then I can also use notation for the co-kernels. So this will be co-kernel of the J of I, and there will be co-kernel of the K0 of I, right? And since on the previous step we have an isomorphism, we can also kind of write 0 here and 0 here. So that's the diagram that we have. Okay, now take an element X in the G of B. So this element has image in K0 of B coming from K0 of A, right? So take an element here, look at this image in the K0 of B. I want to understand when this happens that this actually comes from the element from here. So as image coming from the K0 of A, if and only if X is in the G of A, right? This is just words for this commutative diagram. So take an element here, I can map it here. So I want to know when this is here. So this is if and only if I map it here and get 0. But that's precisely the same thing as I map it here and get 0. So it is in the G of A. Okay, so that's a simple observation about the diagram. And now inside the proof of this theorem, I want to prove a claim from which everything follows. Just kind of reformulate everything. For X in the B, so some object in the B, the class of this object is in the G of A, which we condition we're interested in. If and only if I can take this X, take a direct sum with some A1, get some object A2, for some A1 and A2 being objects in the category A. Okay, So let's prove this. Well, first of all, I think in one direction, if you already know that you have right-hand side for this claim, then clearly you can present this X as a difference of two elements of two classes from A, so you'll get this. So in this direction, I want to say that this is clear. So the non-trivial direction is of course the other one. Okay, so let's take this class of X. As you know, we can present any class of X as the difference of two classes. So where Y and Z are in A. Right? So any class in the G of A can be presented as such difference for objects X and Z in the A. Do this for this class. So then the class of X plus the class of Z, the class of X plus Z is equal to the class of Y. So then there is an object W in the subcategory B. We still have the assumption that the thick of A is B, such that, first of all, I used the lemma that I didn't prove. So there is this W by the lemma that I didn't prove, that the X plus Z plus W is isomorphic to the Y plus W by that lemma. And then by the assumption that the thick of A is equal to B, I can say that there is another object which I'm going to call B in the B, such that U, which is the sum of the V W plus V. So this is in the A. Okay, so I need to take this isomorphism with two sums, also add as a sum this object V, right? And then I'll get exactly what I have on the right hand side, right? So then just simply state the answer. So take A1 to be Z plus U, and take A2 to be Y plus U, right? Since U is in the A and Z and Y is in the A, so A1 and A2 are in the A. Hence, this is the proof in the other direction. So that's the end of the proof of the claim, and now we can return to the theorem, right? And the theorem is now follows immediately, right? So we first of all, this condition that we have in the theorem, I reformulated in terms of the G of A. Now this condition for the G of A using the claim, I reformulated as that identity. But then I can just look at the trivial distinguished triangle. I have A1, right? So this is so A1 is of course mapped to the A2 as a direct summand, so then there will be X, and that's a distinguished triangle, right? So A1 and A2 are in A, hence X is in A, okay? That's the proof. Maybe I give you a minute to think about the proof, maybe you have some questions.
We get the last distinguished triangle. How we get the last distinguished triangle?
It's a topological distinguished triangle since A2 is just the sum
Oh, yes,
of
yes.
A1 and X. Yeah, you can notice that and I proved this theorem only in one direction, right? So of course the interesting direction is only one, right? So if I know this condition for the K0 classes, I want to get the conclusion about the object X, right? Which is in A. But of course in the other direction, if object is already in A, then this is kind of follows immediately this trivial direction. Okay, so let me maybe squeeze in a corollary here. So if X is in the B, right, in the subcategory, plus X shifted by 1 is in the A. Right? So if you have this situation with a dense subcategory, with a one shift, you get an object in A. Right? And X is a direct summand of that object. Well, why this is follows? Well, because you look at the K result. So that's just immediately follows from what we do. And then if you return to what I wrote here about the closure, another corollary, just kind of improvement of the last statement about Thomason localization, is the following. If X is a compact object in the quotient category, compact object in the category S. So that's the improvement of the last statement that I wanted to do using K0. You can take this complement just to be shared by one of the given objects.
Are there any geometric examples of non-thick categories?
Such that the thick closure of subcategory is the category.
Yes.
Well, I think almost any example is the example which is not thick. Or for example, take a scheme,
It's thick. It's not dense.
yeah, it's not dense.
Yes, I want example of dense or not thick.
Yeah, you want an example. You want an example of a general subcategory which is not thick, right?
Yes.
I'm pretty sure that there are examples. They're just not come to mind at the moment. So maybe next week I'll answer your question. But I'm pretty sure that there are examples. Okay, so this is the kind of the course is to prove the famous Brown's representability theorem. Triangulated category. Let's take a cohomological functor, contravariant cohomological functor. So T, H from the T opposite to the abelian groups. It has the property that it maps direct sums to the direct products. Right, that's a contravariant functor. So this is what you expect from such functor. Yeah, so of course, this makes sense if I assume that in the category T I have all direct sums, right? So then I have the meaning of this claim. So then the conclusion is very simple. H is representable. So in other words, there is a natural equivalence of this functor H with the home into some object X. So it's a contravariant representable functor. So the proof will be in the three steps. I construct the object that represents this functor, I construct the natural transformation, and then I check that there's actually a natural equivalence of two functors. So step one, so maybe as a remark, so what we want to show is that the H is a naturally equivalent as a functor to the home to the X. So that's the X that I'm going to show exists. So step one, definition of X. So I'm going to define this X as some homotopical limit and then later check that everything works. So let me fix set T to be the set of compact generators. set of compact generators of the category T. So then I do the following induction. I'm going to define the set U0 to be the disjoint union of the H of T over all elements T in the set T. That's the set. And then I'm going to define object x0 to be the direct sum of the T. And the direct sum is taken over all kind of possible pairs T and alpha in the U0. And so in the U0 kind of have, you can think of this as some sort of maybe as a vibration, right? With the base given by the set T, and in each fiber is just this H of T as a set, right? So this together you get some vibration, and then you kind of take as many copies of this little t in the set T, as many as you have these elements in this set in the abelian group H or T.
Can you repeat what is U0?
This set.
So it is a coproduct?
Disjoint union of sets. So I'm just working with the sets.
Yes. So we consider H
Just the set.
not just an abelian group, but a set.
Yes. Okay, so this is how we define x0. And also I want to notice that immediately I'll get a tautological element alpha 0, which lives in the H applied to the x0. Well, by the definition of x0 and the property of the functor h that we have in the statement, I can rewrite this as the product over all such pairs T and alpha in the U0 of the H of T, right? And this alpha 0 is kind of the tautological element, right? So I need an element in this product. Well, just take the element. Well, if you have kind of this element T comma alpha in U0, right? You take the same element in this product. And in this product, there are a lot of quite tautological things, but maybe you need to think about them a little bit to understand. Is it clear why this alpha 0 exists as a tautological element, right? So I need to, in this product, kind of in each component, I need to write an element, right? I just write an element, which is this one. Right, so this product is parameterized by this set. So I just can take an element with a fixed T. I just take an element alpha, which lives here. So there is an element alpha 0 by kind of which is constructed in a tautological way. And we can use the Ioannidis lemma and reinterpret this alpha 0. So kind of this alpha 0 corresponds to the natural transformation phi 0 from the home, so from the representable functor represented by x0 to the functor h, right? By Ioannidis lemma, natural transformation of functors like this are exactly given by the functor h evaluated on the object x0. So this is Ioannidis.
So what has happened? What is phi 0?
Well, I have an element here, right?
Yes.
By the Ioannidis lemma, elements here are in bijection with the natural transformations like this. So Ioannidis lemma tells exactly that the natural transformations from a representable functor to a functor is the value of this functor on representing object. Okay. So by construction, well, I can look at so I have this natural transformation, and I want to look at the component of this natural transformation, but since I already have this index 0, I'm going to write the object on the top. So this is just a component of natural transformation corresponding to object T, right? So I'm just using a little bit non-standard notation in this book, since I'll get a bunch of natural transformations parameterized by natural numbers, and the lower index is already taken for this. So by construction, if I take this component of the natural transformation phi 0, so this will be from the home T x 0 to the h of t. So this is an epimorphism. So now I do the induction procedure. I'll define all the sets for all the natural numbers. So un plus 1 will be, by definition, the disjoint union, again, over all the complex generators, little t and the t, all the kernels of the maps of the home t x n, given by the natural transformation phi n with the component t to the h of t. So this is the un plus 1, and then I can define coproduct or direct sum kn plus 1. That is by definition the direct sum of t such that f and t is in the un plus 1. And use distinguished triangle, so kn plus 1 as a canonical map to the xn, and then extend this or complete this to a distinguished triangle and denote the cone xn plus 1. So that's an inductive definition of the objects x0, x1, etc. for all natural numbers. Okay. So, and I'm assuming that on each step I'm constructing the map, not the map, I'm constructing the element alpha n, so I constructed alpha 0, and I also want to, since I'm on the step of the induction, I'm using this phi n, which corresponds to the alpha n of the previous step. I want to construct the maps, so I need to construct alpha n plus 1. To do this, I take this distinguished triangle, apply h to this, so h is a homological factor, so then I'll get the h, maybe I'll try to squeeze it here, so h applied to the x with the index n plus 1 is mapped to the h applied to the xn, and this is mapped to the h of the kn plus 1. Now, since this is kn plus 1 is just a direct sum, I can write this last term as the product of the h of t, and the product is taken over all pairs f and t, which are in the un plus 1. So here we have, by induction hypothesis, some element alpha n, right? And I claim that by this choice of the un plus 1, right, if you apply this map from the h of the xn to here, you get 0. So alpha n is mapped to the 0 by the definition of un plus 1, so by the kernels. So it means that since this is mapped to 0, so there is a map alpha n plus 1 that lives here, which is mapped to the alpha n. So all these elements alpha n kind of agree with each other. And if the elements agree with each other, we can equivalently write the statement using Grothendieck's lemma as follows: that we have home from something to the xn. So then there is an induced map home from something to the xn plus 1. So this is mapped to the h, and the square is commutative. So commutative by the constructions of the alphas. And finally, we set x, that's going to be an object representing the functor, to be the homotopical limit of this object's xn. So now we need to show that this is actually a representing object. But the step 2 of the proof. Here I just claim that there is a natural transformation phi from the home to the x to the h, such that I have a commutative diagram. So in this commutative diagram I have three functions: home to the x, which is mapped to the h using natural transformation phi. So then there is home to the xn and the induced map. So there is a map from xn to the x, and hence there is a map on the homes. And here, of course, there is a map phi n. So this is commutative for any n starting with 0. Okay, so let's write the distinguished triangle for the object x. So the direct sum of the xn's, 1 minus mu, direct sum of the xn's, x, and then the shift. So we can apply functor h to this distinguished triangle, and then we'll get h of x mapped to the product of the h of the xn, and this is mapped to the product of the h of the xn. Okay. 3 terms from the longest sequence. So then I claim that if you take this 1 minus mu, the map, and apply this to the product of the alpha n's, this is xn, right? So alpha n lives in this h of the xn, so the product of the alpha n's lives in this product, and if you apply 1 minus mu, you get 0. You just go back to the definition of the 1 minus mu, and since we have this property, right, this property is more or less equivalent to this statement. We can check this, that this makes sense. Okay, so finally, this means that this product is mapped to 0, so there is some element alpha that lives in the h of x, which is mapped to the product of the alpha n's. Right, and this is by Grothendieck's lemma again the natural transformation. So this element alpha by Grothendieck's lemma corresponds to the natural transformation phi, and you can again, little exercise, check that by the construction this the triangle is commutative, which follows more or less by kind of carefully looking at what we've done before. So finally, the last step of the proof, step 3. I want to show that phi is a natural equivalence. So on the previous 2 steps, I constructed object x, constructed natural transformation. I want to show that this is an isomorphism. Okay, so let me call this diagram that I have maybe in star n, because there is such diagram for any n, right? So first observation is very simple. By looking at star 0, we can conclude that phi t is an epimorphism for any t which is a compact generator, right? I just plug in t in this diagram. Since n is equal to 0, I know this is an epimorphism, hence this has to be also an epimorphism, right? If you have a composition of two maps and the composition is epimorphism, the last map is an epimorphism. Okay, so we know that this is an epimorphism for any t. I want to show that this is also a monomorphism for any t. For this, I will take element f in the form Tx, which is, by the definition of the x as a homotopic limit, I can also write this as a direct limit of the t to the xn's. So such that phi component with the object t applied to f is equal to 0. So I want to conclude that f is 0 and hence this is a monomorphism. Okay, so then I claim that there is, since t is a compact object, so that there is a map fn from the t to the xn such that the composition from the t using map fn to the xn and to the x, where I'm just use notation un, the canonical map from the xn to the x. So, for example, that comes from this distinguished triangle. So this whole composition, so such that composition is again f. So is f, and that is true for any n greater or equal than 0. So then I want to say that the fn is in the kernel of the home Txn. So this is a map phi Tn to the h of t. So another, well, this is we get because we know that the phi of t of f is equal to the 0. So in other words, if I consider a pair, so just reinterpreting what I get, pair of the fn and t, so then this is by construction an element in the set un plus 1. So looking back at the definition, well, this definition on that blackboard, we can say that fn factors through kn plus 1, and in particular the composition of the jn and fn is equal to 0. But if you look at the composition of the xn map to the xn plus 1 using the map jn, just jn, and then just the map un plus 1, the canonical map to the, well, no, not really canonical, but the kind of the map to the homotopical limit, then this composition is precisely the same thing as just the map un. So I can write f as the composition of the un fn. Now this is the same thing as the un plus 1 jn fn, but that's 0. So the map f by this kind of computation with the components of this map is 0. So that there is a little, we're almost done. So there is one sentence maybe that I need to say. is that we proved that this is a monomorphism for a fixed little t, right? Epimorphism, monomorphism, so isomorphism for a fixed little t. But I can say that the phi t give me an isomorphism from the home t x with the h of t. So for any t, well, I can say that this is for any t in the set t, but I can also improve this, right? Since both functors commute with the direct sums, I can as well say that this is true for any little t which is in the log of the large t. So that's an improvement since the both functors commute with direct sums. But the log of the large t for any compactly generated category just coincides with the t. So finally, with this simple observation, that's the end of the proof. So there are steps here and there that I left to you to check, because these kind of tautological steps, I think it's better if you see for yourself. But that's kind of the proof modular, several details that I left as little exercises.
Как вы поняли, что fn в ядре лежит?
Here?
Yes.
Well, you already know that this composition, right, is equal to 0. So then, and we know that, for example, you have this commutative triangle.
Mhm.
So just kind of combine this observation with this commutative triangle. Okay. So I want to continue, so if you don't have any questions. Okay, so, and I have a simple corollary. So let's let S be a compactly generated category, and suppose I have a functor f from the S to T, so that's a triangulated functor. That's a triangulated functor, and I assume from this functor, so suppose f reserves coproducts. So then f admits the right adjoint. Yeah, by the way, there's one thing that I want to say before we continue this corollary, is in the proof it is quite important that the categories in the proof of the statement there is only one category, and this category have homes as a sets, right? Because several times we take coproducts, we know that coproducts exist for sets, but they not necessarily exist for classes. So it's important to understand that Brown's theorem only works for the locally small triangulate category. And hence, this is why we need this result that the derived category for Grothendieck category is locally small, right? Because otherwise we won't be able to apply the Brown's theorem to that situation. Yeah, so this corollary, I want to say that this is kind of standard proof that you can find maybe in many books about category theory. So I want to give you a sketch. So we fix T, an object in the triangulated category T. So then the functor that takes an object S and sends this object S from the category large S to the home in the category T. So I by f of S to the T. is cohomological. So cohomological functor on the S. S is compactly generated, and then we check that the conditions of the theorem are satisfied. So if I take the home, which I applied to a direct sum of the, some say, S lambda into some object T, so then, since I know that F preserves coproduct, I can write this as a home of the direct sum of the F applied to the S lambda to the T. And now in the home we can take the polylimit of the first argument and do it out as the limit. So this will be the product of the lambda of the home and the tau of the F of the S lambda T. So that's quite a very simple computation. So for this functor that I don't even give a name, but this satisfies the conditions of the Ground's representability theorem. Hence, this is represented by some object g of t. So, hence, this functor is represented by object which I'm going to call g of t. So, in other words, home T, F of S to the T is isomorphic to the home of the S from the S to the G of T. So this is how we define kind of this functor on the objects. When you can define this for any object little t, then you check that you can define this for the morphisms, and together this thing forms a functor which is exactly directed to it. So this is a pretty standard construction from the category theory. So the details are left as an exercise. Okay, so this finishes our discussion of the homological algebra of translate categories, and now I want to start next chapter of the algebraic geometry. So chapter 6. So now I have actually, to be honest, I have a problem. So let me call this derived categories of quasi-coherent modules or sheaves. Derived category quasi-coherent sheaves. So the problem is that before, in the first 5 chapters, I can assume that you don't know anything about translate categories and just kind of do everything from the very beginning. For algebraic geometry, I'm not sure what you know, what you don't know. So it might be that in the beginning I'm going to say some trivial things that you already know from some other courses, so it won't be very useful. But maybe some of you don't know this. So let me start slowly, and the first section will be OX modules. Of course, I'm not going to define OX modules. I assume that you already know this from the algebraic geometry. I'm going mostly focus on some properties of the derived categories of the OX modules. So first, the beginning is purely topological. So definition, I'm not sure, maybe you know this and it's just a waste of time. So X is a topological space, right? Then you consider a subspace W, which is locally closed. So W is locally closed. So let me also fix notation J. So that's the inclusion of this locally closed subspace into X. So G will be a sheaf of abelian groups on the W. Oh, do you know the definition of the functor J with the lower shrink? Just purely topological definition for this special case where you have an inclusion of locally closed subset. There is a more general version where you can define J with the lower shrink for any continuous map. But for what we do, it's just enough to kind of look for the special case when the W is locally closed, well, then this is by definition just if you compute this on some open set U on the X, right? So then this is just sections in the intersection such that the support of this section is closed in W. Just one standard definition from the topology, shift theory. So, yeah, and in this section, especially in the beginning of this chapter, I want to skip a lot of details. The details I'm going to skip is usually just 1 or 2 lines of computation to convince yourself. So consider this as maybe as a set of very simple exercises. So then, in this way, we can check that this construction is functorial, and we get a functor from the category of the abelian groups on the W to the category of the abelian groups of the X. So this functor has several properties that I'm going to formulate as remarks. So first remark, that the J lower shriek is of some sheaf of abelian groups G is always a subsheaf inside the J lower star of G. So, and special case, if W is closed subset, right, so then this J lower shriek is actually coincide with the J lower star. So the second remark, which again follows more or less from the definition, is that whenever we take a point, little x in the space X, apply this functor J lower shriek to G and look at the stalk at this point, little x, then this is the stalk of the original sheaf G if you choose your point in the W, and 0 otherwise. So for this reason, sometimes this functor J lower shriek is called extension by 0. Especially if you take an open subset. Yeah, so since you know your answer for the stalks of the J lower shriek of G, you can immediately notice that this functor is exact and fully faithful. Okay. So remark number 3, you can again combine 2 definitions and check that if you take the function J inverse, position with the J lower shriek of G, you'll get a sheaf which is isomorphic to the G. Again, just look, you can look at the spots. And 4, also one line computation that I'm not going to do, that you have an equivalence of categories. So you have abelian groups on the sheaves of abelian groups on the W. So in one direction you have J with a lower shriek, in the other direction you have functor J inverse, but then you consider a subcategory, so sheaves of abelian groups on X, supported on the W. So I'm going to indicate this with the index W. So this is by definition all the F of the AB of X, such that if you look at the stalk at some point little x, this is 0, or any little x which is x which is in the complement of the double. So these 2 functors give you an equivalence of categories again. 3 is just a part of this equivalence of categories. So another definition from algebraic topology, if you have a sheaf of abelian groups on some topological space X, you can define another sheaf, a local cohomology sheaf H0, some W of F, and this is on the open subset U is defined as the sections of the gamma, so sections of the given sheaf F over the open set U, with the property that the support of this section is contained in the W. So this is automatically some subsheaf of the sheaf F. And well, for this subsheaf you can take the derived functors, and this is called the local cohomology and algebraic topology. So then, this is kind of the first part of the definition, and the second part of the definition is that I can define functor H with the upper shriek of the sheaf of abelian groups, and this will be just by definition the H upper star applied to the H0 W of F. That's the definition of functor, and why this is a kind of useful functor? Well, because we have a proposition. Well, that's not just a two-line computation, but it's not very hard. You can find this in any book on sheaf theory. Is that you have the adjunction.
H is times G. H is equal to G.
H?
So what is H? Is it J?
Oh, yeah, thank you. Yes. Yes, yeah, yes. Somehow switch to the H. Yeah. H is J. So we have this pair of adjoint functors. So proof this exercise and several other remarks. So for open W, right? So open W is an example of locally closed. Then in this case, J with the upper shriek is precisely the same thing as the J with the upper star. So for open subset, J with the lower shriek is just the left adjoint to the J with the upper star. And yeah, and the one more remark is that, so remark 2 is the following. You take the another special case, Z in X is closed, and you take U to be the complement to this Z. Denote the standard embeddings of the Z to the X by I, and J is the embedding of the U into the X. Let's get the standard topological notation. You take a sheaf of abelian groups on the X. Then there is a functorial short exact sequence. So there is functorial short exact sequence. And you can check immediately that this is exact again by looking at the stocks. So 0, J lower star, J to the minus 1, apply to the F, F, I lower star, I upper star, F 0. So the morphisms here, both morphisms are given by the adjunction, and the exactness you can check by looking at the stocks. Okay, so that's kind of was a quick reminder from the topology that you, I believe, know. Now let's go to the ring spaces. So suppose that I have a X or X. This is a ring space. By the way, in the beginning, from what I'm going to tell you, you can even think that this sheaf of rings is not necessarily commutative. So then, if again I take an open subset U inside X, so then I claim that this functor J with a lower shriek of G, so is, well, I need to take G, so G will be in the modules over OX, so apply this functor, so this is submodule inside the J lower star of G, and this is actually OX submodule. Hence, it means it's not just a topological functor. We can use J lower shriek from the abelian category of the OW modules. So that's a functor from the abelian category of the OW modules. So OU modules in this case, OU to the OX modules. And this can be used to give the following definition. Define object OU sub X. So this is kind of standard notation for an object. To be the J lower shrink applied to the OX restricted to U. Although you can also write apply to the OU, which is just the OX restricted to U. So that would be another notation for the same thing. So take structure shift, restrict this to an open subset space, and take the this proper push forward. Okay, so proposition, probably the last thing we can do today. Yeah. So modules over X is a Grothendieck category. Grothendieck category. Well, first of all, I assume that you already know. So clearly, this category of OX modules is complete and co-complete. So, for example, how we take the limit in this category?
We need to prove that there are kernels and products. So to show that it is.
Yeah. Well, let's start with the products. Why there are products in this category?
We can just take the product and then the certification of it.
Well, I think if you take a product, you don't need certification, you already can get a shoe. But you can check this. I think if you fix an open subset, right, you take all this. For the product of the, say, FIs, on the U, you just take the product of the U, and I think that is already a shoe. So you can check this. But for the co-products, I think this doesn't work. For the co-products, you need to take certification. So you take co-product of the FI on the U, and then you take the co-product. And what's the notation for certification that you like? Well, I know notation where you write something with little a certification. So this is why you have products and co-products, and for kernels and co-kernels, this is I think quite easy. Kernels and co-kernels are again OX modules. And so then the fact that filtered colimits are exact. So in the Grothendieck abelian category, you need to know that the filtered colimits are exact. So this can be seen stopwise. And finally, I need a generator. So for a generator, I can take the following. I take the co-product of the OU inside X that I just defined in the previous definition, and I take U that would be an element in the B. So where in this case B is a base of topology. Right, so this follows, for example, by the following formula. If you compute home from the O U, so U subset inside X to the F, so by using the adjunction, you can do the computation and see immediately that this is isomorphic to just the value of the f on u. So if the home from the G to the f is equal to 0, it just means that f of u is 0 on any open subset which is on the basis of some topology. That's f is 0. So that's the proof that this is a Grothendieck category, and you can see that's not a very interesting statement, it's more just automatic. The statement that the quasi-coherent sheets on any scheme form Grothendieck category is much more interesting. It's much less trivial. Okay, that's all for today. We'll continue next week.